first geological observations in this area were by First Nations people. They discovered valuable stone resources which they traded for hundreds of kilometres. But it's the form of these rocks that is both fascinating and mysterious to anyone that comes to this very special place. This stream, Piper's Creek, has been cutting down through this ancient bedrock to reveal a spectacular folded formation. This magnificent syncline. Alfred Selwyn, founder of the Geological Survey of Victoria, mapped this area in 1852. He would have been fascinated by this fold, knowing the immense forces required to squeeze and buckle these rocks. But what he didn't know is what generated those forces. The mystery to that would not be answered for another 100 years. The shape of the continents has long been familiar as shown by this 1856 map, but it was not until the 1960s that the true nature of Earth's upper layers was revealed. The theory of plate tectonics showed how the Earth's crust is made up of huge fragments of continental and ocean floor rocks, called plates. Over time, plates push and shove against each other, and even pull apart. When plates collide, the immense forces can cause mountain ranges to rise, and the rocks that get caught up in this process, like here at Piper's Creek, are upended and crumpled into a series of folds. The theory of plate tectonics changed our view of the world forever. Professor John Dewey is internationally known as one of the pioneers of plate tectonics. In the late 1960s, he used this exciting new idea to explain how continents grow. When at Cambridge University in the winter of 1964 and 65, he had one of those life-changing moments when he met two of the founding fathers of plate tectonics.
I had the massive good fortune to have Tuzo Wilson on sabbatical leave and Harry Hess from Princeton on sabbatical leave. Harry was great, but Tuzo Wilson was very special.
Within just a few years, John Dewey found himself in North America working to explain the connection between plate tectonics and mountain building.
And I thought, what I'm going to do while I'm on this sabbatical leave in Lamont, I'm going to find out all I can about the Appalachian mountain chain. I knew a lot about the Caledonides. So what I did, I got a gigantic piece of tracing linen, and I got a big drawing table in Lamont. I was given an office with a big drawing table, and I gradually got out all the state maps, Vermont and New Hampshire and Connecticut, and I tried to simplify the geology, and I plotted these up on this gigantic piece of linen that went from Newfoundland to Alabama.
Without a computer?
Without a computer. I didn't have computers in those days.
I met John Dewey in 2009 and recorded 3 video interviews. At the time, I only used a small portion of this material. Now it's time to release the whole interview from one of the founding fathers of plate tectonics.
I grew up in the northeastern suburbs of London in southwest Essex, in a small village called Chingford, which I suppose is about 20 miles out of northeast London, and went to primary school in the area, and all my schooling was in that general area. And my interests as a schoolboy were incredibly varied. I was mostly interested in sport, in cricket and rugby and gymnastics, which I did rather well. But all that time, I was still trying to work out what the heck I was going to do. And until I was 16, I was so obsessed with sport, I didn't really work very, very, very hard academically. But at 16, a housemaster came to me and said, "Look, Dewey," he said, "you're not going to be a great sportsman. You're an adequate sportsman in these various sports, but you're not going to make your living out of these things. You've got to somehow think about a way in which you develop an academic career or a professional career of some kind." And I had a great uncle who was a geologist, Henry Dewey, who worked in southwest England, He was a district geologist for the British Geological Survey in southwest England. I knew of him. I didn't really know him at all well. He was a sort of great uncle, and I was always vaguely interested in geology because my housemaster was an amateur geologist, and I developed a real interest in geology then. But even that didn't fully strike, because when I finished my so-called O-levels in England, I started A-levels in English, French, and German. Because I thought about becoming a journalist. I also love art. I paint. I still paint a great deal. So I had a very diverse and varied set of interests. But then I gradually realized that geology was what I wanted to do, starting from an amateur interest. So I had to work through and I had to switch into science. So I switched into a whole set of science subjects to get into university. And then I went to the University of London and started geology, and it was nothing else from that point onwards.
What do you think it was that really intrigued you about the subject?
I think it was mostly trying to reconstruct history from rocks. I love the beauty of rocks. I've always thought that rocks and fossils and minerals are intrinsically very beautiful. So there's that aspect of it. But mostly, I think, we had a wonderful master at school who was an amateur geologist, and he took a group of maybe 20 boys and some girls and other people from surrounding schools on cycling tours around Britain. We go off for a month. We cycle around Cornwall and Devon or Lake District or Northern Ireland or somewhere, Scotland, and look at rocks. And I was intrigued right from that very early period in, say, what do the rocks mean in terms of what's happened to the planet? How can we actually use those rocks to discern what the Ordovician was like, or what the Silurian was like, or when no plants existed, you must have had soils forming at a heck of a terrible rate, and erosion, and gosh knows what. The history of the planet is very complicated, and it's changed continuously, and I was always interested in that, how it changes.
It's fascinating, isn't it, that there's actually information contained in these seemingly inanimate objects, rocks, and you can reconstruct the past.
The climate. I mean, just look at the history of the climate of the Earth. Astonishing. Only 12,000 years ago, in the northern hemisphere, and in fact much of the Earth, we were coming out of an ice age. We're still coming out of an ice age, of course, and sea level is still rising, whatever we do anthropogenically. But 12,000 years ago, there were catastrophic changes in the Earth, catastrophic changes. And you think about any particular piece of real estate in the planet. It's been a desert. It's been covered with three kilometers of ice. It's been a windswept area. It's been a savanna. Every area has tremendous changes. So the notion of a static planet is a shocking thing. And of course, the planet has not been static. It's changed continuously.
Now, you started your career in geology at a time when some people still found it hard to accept that the continents had moved over time. Now, where were you at this time? What were you doing? And how did this new revelation affect you?
Perhaps I can drop back a bit to the time I went into university, which is almost 10 years, in fact just slightly more than 10 years before the Plate Tectonic revolution. And what happened was this: I went to college like everyone else in those days, and I learned geology but not in a completely different way than the kids learn it today, but I learned it without a paradigm. We basically rocks, minerals, fossils, structures, and a lot of microscope work, a lot of field mapping. We learned the basic skills, and perhaps we can say later that this is one of the troubles with modern geology. I think kids are not learning those basic skills. They're going off into wild hypothesis and model building and all those sorts of things. And as a result, it's very hard to find kids. The oil companies now say that they're finding it hard to get people who know basic skills in geology. So that's the way I learned geology in college, through absolutely basic field geology and lab geology, rocks, minerals and fossils and maps. And that persisted. Then I went to do a PhD in Imperial College in London. I was at Queen Mary College as an undergraduate. Then I went to Imperial College to do my PhD. And in those days, again, the way you did a PhD in those days, perhaps quite dissimilar from the way we do it now, is you're given an area, a quadrangle, a circumscribed area in which the geology is perhaps not very well known, Lots of those still in the British Isles, or it can be abroad. But I was given a patch in the west of Ireland, in which the last map that had been made of that area was in 1872. So I was sent off to this piece of Ordovician, what now turns to be a part of an arc, with rocks somewhat similar to the Macquarie Arc. And I mapped it and did the structure, and you did everything. You did the petrology, the structure, the sedimentology, the fossils if you had them, the geomorphology. You had to do everything. So that was my life as an undergraduate and a graduate student. Then I got a lectureship in the University of Manchester. You sort of progressed. Most people either went into an oil company or went into a mining company or joined a geological survey or went into academia. And I wanted to continue research, so I went into academia, got a job at the University of Manchester.
We continued the conversation late one evening when Professor Dewey talked about meeting two founding fathers of plate tectonic theory.
Yes, I went to Cambridge in '64 and about to continue my sort of basic semi-boring research in geology. Nothing's boring in geology, but I was doing basic geology, mapping and looking at rocks and structures and fossils and so forth. And then I had the massive good fortune to have Tuzo Wilson on sabbatical leave and Harry Hess from Princeton on sabbatical leave. Harry used to come into my room with a cigarette drooping from his lips on many occasions and would teach me about ophiolites and all kinds of rocks that I didn't know about before. But Harry was great, but Tuzo Wilson was very special. I was working away one morning in the Sedgwick Museum in Cambridge, and Tuzo, who I got to know quite well, came into my room and said, "Dewey, he always called me Dewey. Dewey, I have discovered a new class of fault." And I thought to myself, nonsense. We know normal faults, thrust faults, strike-slip faults, transcurrent faults. Those are the kinds of faults we know about. He said, and I said, "Okay, what kind of fault is this, Tuzo?" Sort of trying to humour him in a gentle sort of way. And he said, "It's called a transform fault." "Transform fault," I said. "Is it a kind of fault that's been changed from something else?" "No," he said. "What it does is to transform the motion from one kind of plate boundary to another kind of plate boundary." I didn't really know about plate boundaries in those days, so that was a foreign concept to me. And he pulled a piece of paper out of his pocket. And it was the classic Tuzo Wilson model that connected two ridges with a transform fault. And if you see an offset, normally in geology, if you see a structure here and a structure there with a fault in between, you say that sense of motion has been like that. Okay? In my case, left lateral. In your case, as you see it, right lateral. And he said, no, the motion is the other way around. It transforms the motion of extension from there to there, which means the sense of motion on the fault is that way around. Is right lateral as I see it, left lateral as you see it. And he brought out this piece of paper and he opened it up and closed it and opened it like a concertina. And I realized, my gosh, this is a very clever man, and he has indeed discovered a new kind of fault. And in a sense, that was the beginning of plate tectonics. Tuzo Wilson in 1965 didn't have the concept of large rigid plates. Well, he did in a sense, but he wasn't talking about the motion of rigid spherical caps on a sphere. He was talking about different kinds of boundaries and the way they joined. And he had all the elements of plate tectonics in 1965. And then Mackenzie and Parker, in 1967, of course, developed their concept for the North Pacific, looking at the relationship between the Pacific and North America and other plates. And they used spherical rigid caps and were able to quantify it. Tuzo Wilson had plate tectonics in a qualitative sense, and then it was quantified later by others. A very clever piece of work.
So he must have had an extraordinary ability to think in three dimensions.
Yes. Tuzo had the ideas of oceanic islands, seamount chains, moving over hotspots. Tuzo had a wonderful thought, not a thought experiment, but actually a physical experiment. He said, "Look, John," he said, "if you want to understand, if there's a plume in the mantle coming up and there's a plate moving across it, where you think of it is this. If the plate is moving fast, think of a candle with a piece of paper moving. If you move that paper very quickly across the candle, you see no effect to the surface. If you move it a medium pace, then you can burn a scorch mark, a paleo scorch mark in the plate that gets younger towards the candle, okay? Gets older and older in the direction in which the plate is moving. So there, he said, you can have a mechanism for judging the way in which a plate moves with respect to the mantle underneath. But if the plate is moving very slowly, what happens? The whole plate catches fire, and you have a big volcano on top. And he thought like that. He thought in simple, wonderful, elegant terms.
Back in the vineyard, I asked Professor Dewey to explain some of the main concepts of plate tectonics.
Well, the first observation was by Tusa Wilson and others, and Lynn Sykes and so forth, that earthquakes are not randomly distributed around the planet. They occur in the oceans in very narrow zones, and on the continents in rather more diffuse zones. But nevertheless, both in the continents and the oceans, they are not simply random all over the place. So some process is concentrating faulting and cracking and deformation in those narrow zones. And the obvious concept that came right out of that was that there are perhaps large, rigid, torsionally rigid spherical caps or plates that are in constant relative motion that are rubbing against each other along those and making those earthquake zones. And on a constant size Earth, and we know the Earth from measuring fossil magnetism, we know that the Earth has been, certainly for the last 600 million years, has been a roughly constant size. And therefore, if two plates are pulling apart in one place, they have to be converging in another place. So we have this rather simple and elegant concept of plate tectonics. The plates are these rigid spherical caps, sometimes as thick as 100, maybe 200, 300 kilometers into the mantle. And they are in constant relative motion at a few centimeters a year, sometimes up to 16 centimeters a year, or as little as 2 centimeters a year, perhaps the sort of rate at which your hair and your fingernails grow. That's that sort of rate. And they're constantly moving around. And of course, rocks generally don't deform continuously at those boundaries. We have brittle rocks. And what happens is they get stuck for a while, the plates keep on moving, but they get stuck and then they crack and make an earthquake. So we have this continuous episodic earthquake activity all around the edges of the plates. And that's the concept of plate tectonics. 3 kinds of boundaries. One where the plates are pulling apart, separating, and new hot rock is coming in along the ridge axis.
What's that called?
Seafloor spreading. Good. Seafloor spreading. It's an inappropriate term in a sense because the seafloor is not spreading exactly. It's plates are accreting by new igneous rock being added at their trailing edges. And then so you have those boundaries which form the big ocean ridges in the Atlantic and Pacific and so forth. And then there are places where and they are hot, of course. They're hot, tremendously hot. And then there are places that are much colder where a plate comes along and descends asymmetrically beneath the leading edge of another plate. We call that subduction. And on the leading edge, commonly on the leading edge of the overriding plate, we have these volcanic arcs, perhaps like the Macquarie Arc here, which is probably a good fossil example of one of these things at the edge of the Australian continent during Ordovician times. And then lastly, there are places like the San Andreas Fault where one plate is sliding past another in a strike-slip fashion, a transcurrent fashion. And they all link into a network. And that, what is important, it's not it's obviously not static, but it's not an unchanging network. The plate mosaic constantly changes its form. Where 3 plates come together, triple junctions, they migrate. And the complicated geology triple junctions migrates along boundaries. So you wind up with a very complicated geological pattern resulting from plate tectonics.
And of course it's complicated because we now know the Earth's not flat.
That's true. That means, of course, that, yes, that's a very good point, that if on a flat surface you can have translation. Things can move along linear paths. On a spherical Earth, you have to have rotation. All motions on a spherical Earth are by rotations around an axis that passes through the center of the Earth and comes out of the pole.
That's right. So it becomes a really complex geometrical problem, doesn't it?
It does indeed.
Curved surfaces.
In fact, what is interesting is that I remember when I started off in plate tectonics in adding my name into the plate tectonics game with trying to apply the plate tectonics to geology in the late 60s, early 70s. People were saying to me, "Oh, John, it's just terrible. It's ruined geology. It's ruined geology. It's made geology too simple. You've got all these simple explanations for quite complicated geology." In fact, the reverse is true. I have a phrase that says, "Plate tectonics makes geology as complicated as we know it is." because plate tectonics, although a simple basic idea, the evolution of plate mosaics is actually very, very complicated, the boundaries and the triple junctions, and they produce the most incredibly complicated geology that we see all over the globe.
Well, I must say, it struck me at this conference in particular, the complicated relationships that you get in modern day boundaries. It's a wonder that we can interpret back to the ancient rocks.
Well, that is the trouble. That's the real trouble, of course, that plate tectonics, it generates things, but it also destroys them. Subduction zones take things down the tubes back into the earth.
So we're losing evidence.
Plate tectonics destroys the evidence you might need to, and of course it's not just that, losing it completely, it's scrunching it when two continents. See, there's another complexity. You've got these buoyant continents sitting on the plates, and when one continent arrives at a subduction zone, the quartz-rich rocks of the continents are very hard to subduct. They may go down 100 kilometers and become metamorphosed into high-pressure metamorphic rocks, but you don't get whole-scale subduction of continents. Otherwise, we don't have no continents left, of course. So the result of that is that the squashing mangles things in the collision zones between the continents. So all that already complicated geology gets further mangled, and sometimes it's not just head-on collision. You get a sideways component that smears things out and breaks them into pieces. So I'm afraid geology is a rather complicated subject.
Well, I'd like to come back to mountain belts, but it raises an interesting question about the ocean floors, which tend to be younger than continents. Could you explain the reason for that?
Yes, I think so. As you're quite right to say, rocks in the continents go back to essentially almost 4 billion years, 4,000 million years, or 4 gigayears. There are some places in Western Australia, the Jack Hill Sandstone in the Ilgarn block, in which we've now got zircons that give you evidence of rocks back to 4.2, 4.3, something of that sort. But those are just zircons that have been remobilized and grains, if you like, that have been carried around. So the continents are clearly old. Some parts of the continents are very old. Some parts are very young. It's very clear that in these island arcs, like the Macquarie Arc, it is a very good mechanism for manufacturing continental crust. Because in the island arcs, new igneous rocks come up in the arc and form lavas and things we call plutons at depth, and those are adding volume to the crust from the mantle. And then you slam one of those arcs into a continent, and you've added a big strip of new continent, and that's happening at the present day in Taiwan and various other places. And that appears to be happening certainly for the last 600 million years, and maybe longer. So you can manufacture crust, but of course you can't destroy continental crust very easily, because A, is buoyant, and it's hard to stuff down a subduction zone, and B, it's weak. It's made of quartz. The oceans are made of olivine, and so they're very strong, and the continents are very weak. So when you shove a continent into a subduction zone, it scrumples rather than you get whole-scale subduction. Conversely, the oceans are being generated by one process, seafloor spreading. You're pulling the plates apart, adding new material, and so as you add it at the subduction zones, it's going down the tubes, easily subductible. So there's no piece of oceanic crust older than about 160 million years. About early Jurassic, something of that sort.
And it's basically because the ocean crust is denser.
It's denser. And that's why it sits down, of course. It's dense and it sits down, and it's easily subductible, whereas continents are the dross or froth that are left. And thank goodness we'd be out of business very badly if continents were subductible. We'd have no mineral deposits for a start.
Many of the basic concepts in plate tectonics were developed by scientists studying the ocean floors. But in the late 1960s, it was John Dewey who dramatically extended the new knowledge to continental margins. And in doing that, he showed how mountain belts form. His path to this new understanding was helped by a fortuitous meeting at Cambridge University.
Chuck Drake came from Lamont, Columbia University, on sabbatical, I suppose in about 1966. And he was a great oceanographer, and we got very, very friendly. He said, "Look, John, you're thinking about these sorts of new ideas in geology. Why don't you come to Lamont for sabbatical leave?" So I and my wife and 2 kids came across, and we had a wonderful 6 months in Lamont. And just as I arrived, plate tectonics really exploded. There was Dan Mackenzie's and Parker's paper, Le Pichon from France was there developing his ideas. Jason Morgan had read his classic paper to the AGU, and Isaacs, Oliver and Sykes were writing their great classic paper on seismology and the new global tectonics. And here I was in the center of a hotbed, a ferment of new science. And I was interested in the Appalachian Caledonian system.
Over the previous years, John had mapped and studied the ancient Caledonian rocks in the northern British Isles.
I was terribly interested in how the Caledonian Appalachian chain worked, because obviously when you close the Atlantic, the two come together, and one is clearly is a continuation of the other. And I thought, what I'm going to do while I'm on this sabbatical leave in Lamont, I'm going to find out all I can about the Appalachian mountain chain. I knew a lot about the Caledonides. So what I did, I got a gigantic piece of tracing linen, and I got a big drawing table in Lamont. I was given an office with a big drawing table, and I gradually got out all the state maps, Vermont and New Hampshire and Connecticut, and I tried to simplify the geology. Where were the belts of volcanic rocks? Where were the belts of ultramafic rocks? Where were the rocks we call ophiolites? Where were big facies changes? And I plotted these up on this gigantic piece of linen that went from Newfoundland to Alabama.
Without a computer?
Without a computer. We didn't have, well, I didn't have computers in those days. I was computer illiterate, only recently become literate. And so I developed this huge map of the Appalachians. And from it, I suddenly realized there were belts. There were belts of andesite, belts of tonalite, linear zones that had to be explained in some sort of process happening along a line. And I suddenly realized that the Appalachians somehow, as Tusa Wilson had actually suggested a few years before, was probably a place where an ocean had closed and then reopened, or opened and then closed and then opened up, as like a concertina sort of process. And that's what in 1967 that was what got me going.
Is it fair to say what you were doing was you were applying what had been observed on the ocean floor to what you saw on these lovely maps that you had produced?
Exactly right. I mean, we knew by that stage the concepts of subduction and seafloor spreading and transform faults, various kinds of plate boundaries, continental collisions, collision of arcs with continental margins. That was very clear. So I thought, my goodness, perhaps some of these andesite belts in the Appalachians are island arcs like the West Pacific, and they've slammed into continental margins and become attached. Then other arcs have slammed into those, and then the whole thing closes up with a continent-continent collision. It was very exciting. It was a period when I actually began to use some of my geological knowledge in a sort of broad tectonic way, and it was a wonderful sort of 3 or 4 years at that stage.
The belts of oceanic rocks on John's maps were ripe for a new explanation. No longer could the prevailing geosyncline model explain these observations.
Things line belts. It's got to mean something. It can't mean geosynclines in the classic sense. They simply don't work. And then plate tectonics hits me right in the middle of the head with a fist as I was developing this stuff, and suddenly I realized, my gosh, plate tectonics must explain that Appalachian Caledonian system during the Paleozoic. So I was in the right place at the right time. I went back to Britain after that and I was very excited and tried to persuade people this was phenomenal, my geological friends, and they simply weren't interested for quite a number of years until the early 70s. And then in the early 70s, gradually the ideas were accepted and people started developing.
So it's interesting, there was a much more lively scientific inquiry in America at that time. Is that right?
Oh yes. Except funnily, continental drift before plate tectonics, lateral motion of continents, opening of oceans. It was often said in the 20s and 30s, if you believed in continental drift as a young man, you would never get tenure in an American university. And they say now, of course, if you don't believe in plate tectonics, then belief is the wrong word, of course, but if you don't accept plate tectonics as an idea, you couldn't possibly get a job now. If you're espousing an expanding Earth or a contracting Earth, you simply would be laughed out of court, and quite rightly. Whereas in Europe, I'm not saying that continental drift was the paradigm in which we viewed all of geology, but it was accepted in a strange way. I mean, I was taught by a very amazing man called Hollingworth, who was professor at University College London in the 50s and 60s. And he was a great continental drifter. Lester King from South Africa came and gave lectures, and people said, oh yes, continental drift, very sensible idea. But in North America, it was anathema. It really was. And there was a sudden change in North America in the middle 60s from a very anti-continental drift view to a plate tectonics view. It suddenly happened very rapidly.
What caused that change?
Oh, I think it was mostly oceanographic data. Maurice Ewing at Lamont and others were beginning to explore the oceans and looking at the shapes of the bathymetry of the ocean floor, earthquakes, piston cores in sediments and so forth, and magnetometers were towed behind boats, and gradually the data became overwhelming. And I think it came out of plate tectonics came out of the ocean, not out of the continents. Continents are the sort of dross left behind on top as plate tectonics in the oceans works. And you'd never get plate tectonics out of the continents, very obviously. It comes out of the oceans.
Yeah, so the really important original concepts did come out of the oceans, as you say, but what you did is you took some of these ideas to the continental margins, or the mountain belts at least.
Yes. Yes. It was a way of looking at belts like the Urals, the Appalachians, and the Caledonian belt, and saying, look, here are belts that look like continental margins, look like island arcs, look like collision zones, and it made immense sense. But, then as now, there's this tremendous problem. You have plate tectonics as a large-scale mechanism, and yet it's very, very difficult to use plate tectonics to find mineral deposits, you can explain local geology, you can explain regional geology perhaps, but if you want to understand geology properly, you can't simply have a plate tectonic model and say, that will suddenly explain this area. You've got to work from the grassroots upwards with the geological data of mapping and rocks and minerals and fossils and so forth, and you build models gradually. And of course, we're victims, as I always say, of the inversion problem. It's terribly easy to build models that forward model and say what should be happen if such and such a plate scenario evolved. If you were to take any rocks within the continents and say let's build a model from those, there is no unique model you can easily build from the data. So working from data to models is very, very difficult. Working from models to what the data might be is very easy.
Now, John, I'm really interested in the length of time that it takes to form a mountain belt. Could you comment on that?
Yes, something that's exercised my mind considerably over the last 10, 20 years. There are several kinds of mountain belts. There are those, let's say, like the Andes along the western side of South America, that appear to be related to rather like the crumpling of the prow of a ship, in which the South American plate is crunching westwards, moving westwards in the mantle reference frame, and it's driving into the subduction zone, driving into the trench, so it's in compression. And that causes tremendous uplift and thrusting and crustal thickening and so forth. And that in the Andes, of course, is combined with the building of volcanoes. So the crust is thickening up and thickening up all the time. That kind of mountain is intermittent, but it can last an awful long time. If that westward motion persists, keeps on persisting and persisting, then the mountain will grow and be eroded for as long as that motion takes place. But that motion can stop, of course, and you can have rollback away from the edge, and that'll go into extension, pull the mountain down. But episodic up and down of the Andes has probably been going on for, well, certainly 500 million years, something of that sort. So they can last a long time, in which individual phases of compression can be as short as maybe 10, 20, 30. Then we have another kind of mountain belt that's related to the collision of island arcs, volcanic arcs, with continental margins. And when they slam in, they slam in, and what happens is that the subduction zone is choked by the continental crust as it goes down. So that stops that motion. But we still have ocean out here, behind the arc. So what happens is something Dan Mackenzie suggested years ago, that you get a flip in polarity. The subduction now goes the other way, under the continent. So what you've done is to add an island arc to the continent, increase the volume of crust, thereby doing so. And that kind of orogeny, or mountain building process, generally takes 20 million years or less. It's geologically very, very short. Then lastly, we have orogeny, let's say, like that in the Himalayas and Tibet, where the Indian continent has been grinding progressively into Asia, squashing it. That's lasted 45, 50 million years. So it depends on the kind of erosion, the kind of plate boundary. As short as 10 maybe in some places, and as long as 40, 50 in others.
So what's going to happen in the future in 1 billion years? Are we going to end up with an old wrinkled Earth full of continent and no
Wonderful
ocean?
question. I mean, certainly heat flux is progressively diminishing because of the decay of radiogenic elements. If you take an average half-life for all the radiogenic elements, then the heat flow curve for the Earth is an exponential curve. So you're during the Precambrian, the Earth was losing heat very fast, but we are still losing heat. And eventually, one presumes, the engine will run down. You run out of radioactive material, no more heat. And plate tectonics, basically, is the mechanism by which heat escapes from the planet. You make a plate, you cool it down, shove the cold stuff back into the Earth to cool it off again, get rid of the heat. And so plate tectonics is the principal way, and if you run out of heat, you're going to run out of plate tectonics. When that'll be, I'd have no idea.
Now, I'm interested in your attitude to mapping. You know, you've spent a lot of time thinking at the large scale, global scale, in fact. And I wonder, what's the point of field work if you are thinking at this scale?
Well, my view is that without detailed geological mapping, you don't have a data source, a series of data sources to put together to build the large scale. I mean, you can look at plate tectonics in a geophysical sort of way, seafloor spreading anomalies and earthquakes and volcanoes and all those kinds of things, but that's pretty unsatisfactory in terms of understanding the Earth. It'll give you the broad picture, but you have to remember those plate boundaries are made of rocks. And in order to understand the details of the timing and the processes that are going on that allow a mountain belt to form, for example, how does it happen? I mean, you say it squashes the rock. Well, it squashes the rock. By what mechanism? And the only way to find out is to make detailed geological maps and structural studies in those deformation zones. So I think it's absolutely essential to do ultra fine-scale geological mapping. Out here, for example, in the Macquarie Arc, you need fine-scale geological mapping to find new extensions of ore deposits. And I mean, I'm quite surprised at the lack of very, very detailed maps in the Macquarie Arc. I mean, it's all been mapped at a scale of, I don't know, probably 50,000 or 100,000, something like that. But really, and it's been mapped at locally in great detail around mines. I mean, very, very, very large scales. But I think we need that intermediate scale for regional mapping to really answer a lot of questions that people are trying to ask about the Macquarie Arc. So geological mapping is really the foundation of your database. Without that database, you really can't do anything in terms of mineral deposits, in terms of orogenic processes, volcanoes, earthquakes, all those kinds of things. It's the rocks. Rocks never lie, basically. They may confuse you. You may find it very hard to extract the truth from them, but basically that is the ultimate data source, the rocks themselves.
Well, essentially, that's where all these ideas came from in the first place.
Absolutely, absolutely.
Now, you've travelled the world, worked in different continents across both sides of the Atlantic. Just how important do you think it is as a geologist, to look at rocks in different continents?
I think it's very important to make comparisons. I mean, one can sit in a small area and make detailed geological maps, and gradually you'll understand more and more about the history of that particular piece of crust. But if you want to understand the processes that generate that particular piece of crust, analogies are very important. Comparing with the same sort of thing that's happening in another part of the world. Is this a unique phenomenon, or is it happening elsewhere? So getting around, seeing a lot of rock is very important. H.H. Reed, the great British granite petrologist, years ago said that it's not quite true, but it's not a bad statement, the best geologist is the person who's seen the most rocks. And I think there's something in that, but not just the most rocks around the world in different environments, and also not only in the old rocks, but at young plate boundaries. Study the processes that are happening at young plate boundaries as well. So I think international travel is really very, very important for the aspiring young geologist.
But are there any traps in comparing modern rock situations with old, ancient fold belts?
Some very severe traps. And they are that We're virtually certain that plate tectonics has been happening in pretty well its present form for the last 600 million years. That is from the Ediacaran period, the Pound Quartzite in South Australia. From that sort of time onwards, we've had platforms, we've had lines that are clearly arcs, we've had ophiolites that are lumps of sea floor, we've had blue schists that are high pressure belts and linear belts, a lot of linear arcuate tectonics that looks like plate tectonics. It must be plate tectonics. Prior to 3.1 billion years, I think it's pretty clear that plate tectonics in the Earth was not operating. That is, in the early Archean. The so-called granite greenstone belts like Pilbara and Ilgarn, and maybe parts of the Gawler Craton if there are any old rocks in there. That is a very, very different kind of geology. It's blobby. It's not, you don't get linear belts. It looks as if great masses of heavy lava have sunk into the crust, while the lower crust, the hot lower crust, has risen in great diaperic masses. So blobby, vertical tectonics. Now, from 3.1 to 0.6, I am very confused. And I think most people are confused. You can sort of force plate tectonics into, modern plate tectonics, into some of these belts. You say, look, here's a belt of something looks like a belt of andesites or tonalites or something, or a belt of something. Ah, that must be an old volcanic arc. That must be in subduction. But the trouble is, in the Precambrian, prior to 600 million years, you can't find, or let's go a bit further, 700 million years or thereabouts, you can't find ophiolites, proper ophiolites, you can't find blue schists, you can't find obvious, really linear arcuate belts of andesites. It looks like something is different in there, and maybe there's some kind of evolving tectonics that starts at the end of this early Archean period and gradually evolves into modern plate tectonics. There certainly is lateral motion between pieces. Sergei Pisareski, who's at this conference, has shown very clearly that in the Precambrian there is lateral, from paleomagnetism, there is lateral motion between blocks. So that must mean lateral motion, but that doesn't necessarily mean plate tectonics.
Now that leads me to a more general concept about models. What do you think constitutes a good model? For example, at what point do you abandon a model or move on?
A good model is one, and remember, most models, like plate tectonics, they're not belief systems. Do you believe in plate tectonics? It's not that I believe in it. It's simply the best paradigm or best model that we have at the moment to explain the data we've got. It doesn't mean to say it's right. As Popper said, all you can ever do is prove things wrong. You can never, ever prove things right in science. It's just you simply go with the model that explains most of the data. And that's like plate tectonics. So I say a good model is one that keeps on explaining more and more data. As you find out more and more, that model appears to explain the data. But if you have one major piece of evidence of some kind that contradicts a model, you've then got to, I'm not saying you throw the model out immediately because you may have the data wrong or you may have misinterpreted in some way, but if you start finding lots and lots of things that say, look, that cannot be right, then you must abandon. Tuzo Wilson was a great man in this respect. I once asked Tuzo Wilson, the great Canadian geologist, geophysicist, Tuzo, how many ideas do you think you've had in your life? He said, oh, hundreds. And he was not a modest man necessarily, but and I said, well, how many of those ideas have been right, do you think? Hard to say, but maybe, if I'm lucky, 5% of those will turn out to be, and that's not a bad batting average. And he was prepared to just throw, he has a good idea, what he thought was a good idea, something comes along, says it's not right, gone, throw it up.
I guess in a way it's like mind games, isn't it? It's a process which you can test something intellectually and then move on.
Yes, exactly. The amazing thing actually in terms of modern geology or modern earth science is that plate tectonics arose very rapidly in the 60s from the early evidence of seafloor spreading, Vine and Matthews, and then through Tuzo Wilson's ideas about transform faults, and then Mackenzie's 67 paper. I mean, by the time we got to 67 and 68, it was really a pretty well nailed down hypothesis of some kind. Not proven, but very well nailed down. And since that time, in the last, 40 years, it's got better and better and better. But plate tectonics is not something that has to be applied simply. During the early 70s, everyone jumped on the bandwagon and tried to use plate tectonics to explain everything. Also, plate tectonics is very complicated. it generates complicated geology. So the day of the geologist is not gone. In fact, it's the very reverse. Plate tech, nice simple idea. How does it really work in detail at those plate boundaries?
So we still need feet on the ground.
We need feet on the ground, and we need our students trained in universities, which I'm afraid is progressively diminishing. The amount of field geology that's being taught, making geological maps, we have less and less kids coming out of university who can actually pick up a rock, identify it, or say roughly what that rock is, what it means, can't identify fossils, minerals, and so forth, and they can't make geological maps.
And yet
it's very serious.
And yet that's primarily what attracts young people to something like geology.
They love the fieldwork. I think the science is being taken over. I dare say I might offend a few friends by saying this, but the science is being taken over by people who don't have that geological background. Very good scientists in their own right, geophysicists, geochemists, all kinds of people who don't go in the field very much, don't make maps. And I think many of them, I'm not saying despise geology as such, but they don't recognize the immense complexity of the science and its role in understanding plate boundary tectonics, for example. And they tend to sit in front of computers building models, very useful, but the trouble is they then begin to believe those models. And that's really quite serious, a serious problem.
And science is really exciting. And now sometimes as a scientist, you might have worked on a problem for a long time, gathered the data, and ideas start to fall into place. What does that feel like when it really starts to work for you?
Fantastic. It is absolutely fantastic. And I think the best period, I've had two sort of eureka moments. I mean, I think I've explained a lot, gradually, progressively. This bit of geology, that bit of geology, and it's been great fun. And pushing geological data into plate tectonic scenarios, and that's been great. But that period when I was at Lamont on sabbatical leave in 1967, I was there for six months or so. It was absolutely phenomenal because I was learning about plate tectonics rapidly by the people who were generating it, going to the AGU meetings and GSA meetings and so forth. And at the same time, I was building this big model for the Appalachians, and the two were just melding together just unbelievably. And one was making sense of the other, and it was just a little iterative, continuous feeding process and then I've had a couple recently. One really nice one that I just had with Jack Casey, one of my old students, who's now professor and chairman at the University of Houston Geology Department. We think we've got a model that really works for the rocks we call ophiolites at last. We think we'd really know how ophiolites form. And when we sat down, we were drinking a bottle of wine in Houston together just after a meal and looking at some reconstructions of Southeast Asia. And we had the same idea, looking at the same data at exactly the same time. That was a eureka moment. It was absolutely wonderful. So we're developing that model progressively now. And it's one that appears to be getting better as we talk to people and we get more and more data and so forth. It's solidifying. Not necessarily right, but it's something that seems to work rather well.
I'd just like to change direction just a little bit. What role do you think that the sense of aesthetic or beauty plays in a science like geology?
I think beauty plays a role in all sciences. I think sciences are fantastically, because it has to be the ultimate truth eventually. I mean, I'm not religious, but I respect those who are. But I see tremendous beauty in simply rocks. You go to an outcrop and see a beautiful fold. It's aesthetically massively pleasing. Or in a piece of rock that's been weathered on a shoreline into a fantastic form, immensely beautiful. And so there's the immediacy of beautiful objects, beautiful minerals, beautiful fossils and so forth. It's lovely. And I've got a massive collection around the house, scattered all over the place, of rocks, minerals, or fossils. Not because they're a scientific collection, but I pick them up for their intrinsic beauty and interest. But beyond that, the ideas themselves are beautiful. I mean, plate tectonics is just an incredibly refined, sophisticated concept that has an incredible intrinsic beauty because it works so well. Things that really work well. The atomic models, some of the modern ideas in cosmology. I think cosmology is a fantastically interesting area of astronomy and physics at the present day because they're pushing the boundaries out all the time completely. New explanations of shrinking and expanding universes. It's just wonderful. Wormholes and black holes, and fantastic. It's very exciting.
Now, I know that you're interested in painting. And of course, as a geologist, you learn very quickly to think in 3 dimensions. I'm just wondering, have you ever tried sculpture?
Yes, but it's something that for some reason I've never got on with. I've tried wood carving, and there's a little bit of stone carving at one stage, but I've never got on with it. I like it's very difficult, actually. I think sculpture is perhaps the most difficult form of art, of the arts, because you see some of these wonderful Roman marble heads. You've got to have the object in your mind completely as you chip away. You chip away the wrong bit, you're wrecked, astonishing. But in painting, you can go over things. I paint both in waters and oils. Watercolours have a lovely fresh immediacy, and I like doing that if I'm painting quickly. But I also like large landscape oil paintings where I can work at a painting a lot. So I'm halfway between realism and impressionism. That's my style. But sculpture, I'd love to do it, but I'm not good enough. I can't do it.
Now, if you're wanting to encourage young people to take up science like geology, or the earth sciences in general, what would you say to them?
I'd say get out in the field with somebody who knows some geology. Find somebody in your area, in your region that knows a bit of geology, and persuade them to show you landscapes and rocks and minerals and fossils. Even in a local village around Orange, my gosh, there's wonderful geology around here to look at. So do that. Also, try and get a simple description of the geology of your region, of your area, so you can get into understanding the rocks through that description. That's not always easy, because I'm not sure, for example, there's the geology of Orange, a simplified geology of Orange. But that I like to persuade some of my friends to write those kinds of things, because that's a sort of thing that would excite local school kids. So those two things, and then also make a collection. Start collecting rocks, minerals and fossils, because you can bring them home, you can look them up in books. Buy some simple geology textbooks as well, a nice introduction to geology or something of that sort. So those three things. But also, learn other basic sciences. Don't just learn geology, because in spite of what I said about the model builders and so forth, that's a terribly important area of modern earth science. We can quantify things now in ways that we couldn't even dream of 20 years ago. High-speed computers, for example. You can build models that would have taken years and years to build 40 or 50 years ago. So learn maths and physics and chemistry as well, and learn some biology. So learn geology plus the other sciences.
Well, thanks very much, John.
You're most welcome. Most welcome. Thank you.